light. Give a huge round of applause for Jennifer Wright!
Sorry guys, just need to put my various bits down. Right. Okay, hi, my name is Jenny, and I'm an experimental physicist. Sounds a bit like the start of an AA meeting, but hopefully the rest of the talk won't be like that. Okay, so today I'm going to talk about 8 things you hopefully didn't already know about light. And I'm going to start with fact 1. So light can be used to measure things. This is kind of what I do in my research. So the simplest thing that I'm going to talk about first is how you can use light as a ruler. So I don't know if any of you have heard of Einstein. Put your hands up if you have. That's relieving to hear for the rest of my talk. So basically Einstein came up with the theory that light is the fastest thing, the fastest speed that anything in the universe can travel at, and also that it doesn't matter who you are or where you are in the universe, light will always travel at the same speed in empty space. So it's kind of a bit like a universal speed limit type thing. And this makes it very useful for measuring things. So basically, if I have this simple system here, so I have these very high-tech looking mirrors that I've drawn here, which was very difficult, I assure you. So we have one here and one over here, and we have this laser beam, it's definitely a laser beam, traveling between the 2 mirrors, bouncing between them. And basically what we do is we have a stopwatch, or something a bit more sciencey than a stopwatch, maybe a bit more accurate than a stopwatch, and we measure how long the light takes to bounce between the 2 mirrors, so how long one bounce takes. And because we know the speed of the light, because it's always the same, we can work out the distance between these mirrors really, really accurately. And yeah, this is probably the most accurate kind of way of measuring a distance. So that's the first cool fact about light. So the next one that I'm going to discuss is light has a couple of personality issues that you sort of learn about when you're a physicist. So it's kind of got a split personality. It's not sure if it's one thing or another thing. And basically the best way, or maybe not the best way, but the way I'm going to explain it is with a conga line in a picture from the 40s. So this is kind of what I assume parties look like, I think. So if you're at a party and you decide to join a conga line, then the conga line will probably snake around the room a bit like this, and it'll wiggle around. And this kind of looks a bit like a wave. So if you turned it the other way up, it would be like this. And so kind of like waves on the sea. So that's one aspect of light, it's a wave. But then this conga line is actually made up of little individual people with minds of their own. And it's the same with light. It also can be thought of as being made of little bits of things called photons. So it's actually made of particles. So you can think of it as a particle or you can think of it as a wave. But because it has this dual personality, sometimes you need to take both these things into account. And especially the particle property of light is kind of a problem for me in my experiments. It kind of annoys me a little bit. And that kind of leads me on to my third fact. Okay, so these like little bits of light, these photons, they're a bit like party crashers. They come into my nice, sophisticated 1940s party, and they barge into the conga line like this sort of weird frog that I've got here, and this weird drunk guy here. The wonders of like clip art and things like that. And basically the problem is that these bits of light, like people in the conga line might sort of join the conga line and then leave randomly from the middle or from either of the ends. You don't quite know exactly how many people will be in the conga line at any one time. You just know the vague overall shape of the conga line, and you know that it'll keep on being a wave and snaking around the room. And this is kind of a problem if you're using light to measure things, because it means you get bits of light where you don't expect them to be, which is a little bit confusing. Okay, and this is a big problem because of fact number 4, light is a bully. So I've got this very good illustration here that I quite like, but also it isn't very powerful, so this might not be that obvious, but I've got a torch here. So if I shine this torch, oh, thank you. If I shine this torch at my hand, then some light hits my hand, but because it's not a very powerful torch, I don't really feel any heat from this beam of light, and I also can't really feel it doing anything to my hand. But if my hand was a lot lighter, and this beam of light was a lot more powerful, then I would actually feel my hand being pushed away by the light. And it's quite a weird thing to get your head around, but light kind of pushes objects, which is a lot of the point of what I do, is pushing things with light, or stopping light pushing things. Yeah, so I'll just put my handy torch away, if I can turn it off, which is doubtful. And then get my pointer back. So I go on to the 5th fact of light, is basically that instead of light pushing things around, I can use it to hold things very, very still. So if I go back to the system I had before, where I have one mirror here, they look a bit more like mirrors this time, and another mirror here. So light can be reflected from these mirrors, or it can be transmitted through these mirrors. So over here, I have what is clearly a laser and not a red explosion. And light goes through this mirror, all the way down here, and it can either go through this mirror or bounce back off and go that way. And the way we set up our experiments is we make sure the distance between these two mirrors only lets a whole number of waves of light fit in between the two mirrors. And basically what this means is the light, instead of just going straight from outside the mirrors all the way past and through this mirror, the light will kind of bounce between the two mirrors. And that means, because it bounces between these two mirrors many, many times before it goes out that way again, this means that there's a lot of light power between our two mirrors. And this is actually how we make something called an optical spring, which is essentially a ruler made of light. But I'll talk about that more with my 6th fact. So I'm going to leave the innuendos out, because I think you can probably make them yourselves with various words on the slide. But basically, we can make these optical springs really, really stiff, really, really hard, so that our mirrors don't move very much because they're being held together by this spring, or by this kind of ruler made of light. And a good analogy is if I get a volunteer from the audience, someone near the front, it's really not, I'm just going to do something short, it's not going to hurt, nothing bad will happen to you. Yep. So if I hold this here, and you hold the other end, okay, so my hand here is a mirror, that hand is another mirror. Yeah, and this is the light traveling between the mirrors. So if I push on this mirror, then it pushes your hand back. And that's essentially all that's happening with this optical spring. But if you imagine this is a rod of diamond and not a slightly grubby looking plastic tube, then that's kind of the effect I'm trying to get across. So if you just sit back down, thank you very much. I'll just go back to this one. So basically the reason we want this really hard thing made of light is so we can have this really accurate ruler, so we don't get our mirrors being pushed around by little photons being where they shouldn't be, and we manage to measure these really, really accurate distances between mirrors. And then I'm going to move on to the 7th fact I have. So basically, this is the only kind of biology type image I have in my presentation, just for the biologists in the audience. It's a brain. But basically, light can remember where it's been. So I guess if we go back to the party thing, light clearly doesn't get that drunk because it can remember what it did last night. And basically, if light is traveling through some space and something about that space changes, the light will remember what's happened, and we will be able to tell something about the space and the change that happened to it from the light that has traveled through it. So this brings me on to my last fact, and basically the point of my research. So Einstein, who I was talking about earlier, he predicted something else. So he said this thing about light, and he also predicted stuff about gravity. So gravity is kind of the force that holds everything that is made of something together with other stuff made of something. So it attracts things towards each other. But this other thing that happens is if you get these really dramatic, really fast events with massive stars in space, then sometimes it's a bit like someone's thrown a stone into a pool of water, where the pool of water is all of space, and the stone is this big dramatic event. And you get these kind of ripples coming out from this dramatic event, and they're ripples in actual space. And basically this means that our very accurate ruler or spring that we've made with light over here actually will get stretched or pushed together by this sort of these ripples in space. And essentially all my research is to do with building these kind of rulers and trying to make them as accurate as possible. And yeah, it's really cool and I like it. And that's the end of my talk.